In Module 60, we're going to start examining Dalton's law. So Dalton's law basically looks at the total pressure of a system based on their partial pressures. What I mean by this is that gases, remember if something's in the gas phase, it has how do I say this? Not the most energy it can have, because you can heat up gases, you can make gases hotter, but they're at the highest state, like physical state, for the energy they have. So solids are at like the lowest energy state for the molecules to be together, then liquids are in the middle, gases are at the top of the line for energy. And so that means that the gas particles are moving around, they're not really interacting with one another. They have so much energy that they don't need to be dependent upon forces holding them together. We're going to talk about that in another chapter. It's called intermolecular forces holding the compounds together. Instead, they behave as individual molecules or individual atoms in the gas phase. And that's why gases have no fixed shape or volume, because they're not being attracted to the other molecules to stabilize their energy. They have enough energy that they're just bouncing all over the place. When we look at a total system that's comprised of multiple gases, the total pressure of that system is due to the individual, what we call partial pressures of each individual gas. Partial pressure being the pressure from that individual gas. Because the gases don't rely on each other, don't really interact with each other, we call them their partial pressures, a partial pressure for each individual pieces, and all of those added together make up the total pressure of the total system. So P total is your total pressure of your system, and this is equal to your partial pressure of your first component plus the partial pressure of second component plus the partial pressure of the third component, and so forth. We can also say your partial pressure is equal to your mole fraction times the total pressure of your system. Your mole fraction is basically the percentage of the sample that's comprised of that specific compound or molecule you're looking at, but in a fractional form instead of percent form. So you do need to know the definition of a mole fraction, be able to calculate mole fractions of the components in a mixture, and then use Dalton's law of partial pressures involving gases collected over water. We'll do some examples with that as well. So Dalton's law of partial pressure. The pressure of a mixture of gases is equal to the sum of the partial pressures of each gas present. The specific definition of partial pressure is the pressure that an individual gas in a mixture of gases would exert if it were by itself at the same temperature and volume. So an easy way to express Dalton's law is like this. The pressure total is equal to the pressure of each individual piece. A more useful definition of Dalton's law is that the partial pressure of A is equal to the mole fraction of A times the total pressure of the system, where mole fraction, X sub A, X sub A is your mole fraction, and that's equal to the number of moles of A being whatever component you're looking at, divided by the total number of moles of the system. So again, mole fraction of A is just like percent. We just don't put the percent in there. We don't need it in percent form. So for example, in air, we've got about 78% nitrogen, and then O2, CO2, and argon make up the bulk of the rest of the air that's around us. There's other components that are a smaller percentage, yes, but the bulk of it is N2, or nitrogen gas. Therefore, the mole fraction of N2 in air is equal to 0.78. 78% of the molecules in air are N2 molecules. If the total pressure of the system, or the total pressure of the air around me, was 1 atmosphere, the partial pressure due to just nitrogen would be equal to 0.78 times 1.00 atmosphere, which is equal to 0.78 atmosphere. Another question I often get asked from students is, Why is there not units on your mole fraction? Well, to be honest, it's because you're dividing moles by moles and the units cancel out. So no, there are not units on mole fraction itself. So easiest way to understand this stuff is to apply it. So let's work some examples. So for the first example, we've got two parts to it. A 10-liter container contains a mixture of helium, neon, and argon gases. At 125 degrees C, the mixture has a total pressure of 842 millimeters of mercury. The partial pressure of helium is 451 millimeters of mercury. The partial pressure of neon is 114 millimeters of mercury. The first thing I want to know is what is the mole fraction of each gas in the mixture. So, just to remind us what we've got helium, neon, and argon gases. We are at 125 degrees Celsius with a total pressure of 842 millimeters of mercury. And helium is 451 millimeters of mercury, neon is 114. Now that we have all our parts, let's think about what we've got here. We want mole fraction. I know that the partial pressure of any component, let's say helium, is equal to the mole fraction of helium times the total pressure of the system. I currently have this value and this value. So I'm going to rearrange this equation to solve for the mole fraction. So the mole fraction of helium is going to be equal to my partial pressure of helium divided by my total pressure of the system. My partial pressure of helium is 451 millimeters of mercury. My total pressure of my system, 842. Millimeters of mercury. And let me check that because I wrote down 852 in my notes. I want to make sure I have the right answer here for you guys. 0.536, and then there's no units there because this is a mole fraction. I've got millimeters of mercury divided by millimeters of mercury. I'm going to do the same thing to solve for the mole fraction of neon. Pressure of neon divided by the pressure total will be equal to 114 millimeters of mercury divided by 842 millimeters of mercury gives me 0.135 for my mole fraction of neon. Now I'm on to my mole fraction of argon. I have two ways I can solve my mole fraction of argon. The first, I can think about the fact that the total pressure of the system is equal to the partial pressure of helium plus the partial pressure of neon plus the partial pressure of argon. With this in mind, I can rearrange this equation and solve for the partial pressure of argon. So I've got 842 millimeters of mercury for my total pressure minus 451 millimeters of mercury. So this is total. This is for helium. Minus 114 millimeters of mercury due to neon. This gives me a partial pressure of 227 millimeters of mercury. And that is for argon. So now I can use the equation I was just using, and I can say, okay, my partial pressure of argon, 227 millimeters of mercury, 277, I apologize. That should be 77. (277) millimeters of mercury divided by 842 millimeters of mercury gives me 0.329 for argon. The other way I could solve this problem is understanding that I only have helium, neon, and argon gases. Therefore, the three pieces have to add up to a total value of 1. So the mole fraction of argon would be equal to 1 minus the mole fraction of helium minus the mole fraction of neon. 1 minus 0.536 minus 0.135 gives me 0.329. So you can do it either way. I don't care which way you do it. It does not matter to me. Both of them are going to get you the same answer. But in summary, the mole fraction of helium is 0.536. The mole fraction of neon is 0.135. And the mole fraction of argon is 0.329. So we've answered the first part of the question. What about part B? Part B asks me, what is the mass of argon present in the mixture? So the way I'm going to solve this, first I'm going to give her some room. Sorry, these slides were definitely designed to be on a whiteboard. Didn't try to catch that box. Sorry, you guys. Okay. So to answer part B, the first thing I want to do is I'm going to use Dalton's law to determine the partial pressure of argon. Now I did do that right here, but if you had gone this path instead, you would need to do this first. We find that the partial pressure of argon is 277 millimeters of mercury. And again, to do that, I followed this path, where the pressure total is equal to the partial pressure of the system. I know 2 of the 3, so I solve for the other one. You could also solve this by saying, I know that the pressure of argon is equal to the mole fraction of argon times the total pressure of the system. So 0.329, which is my mole fraction of argon, times my total pressure of my system, 842 millimeters of mercury. And I would get the same answer, 277 millimeters of mercury. So whichever way you're more comfortable with, I don't care. Doesn't bother me either way, but pick which way makes more sense to your head. Now that I have my partial pressure, I'm going to go ahead and use the PV equals nRT equation, or the ideal gas law, to go ahead and calculate the number of moles of argon I have. I want to get to mass of argon. I need to get to moles first. So second, use PV equals nRT to determine moles of argon. So the pressure of argon times the volume of the total system is equal to the number of moles of argon times R times T. The volume and temperature of all gases will be the same, because remember, gases are going to expand to their total container, so we don't have to split up the volume between all the gases. All the gases are using the whole container, and all the gases are at the same temperature. I'm going to rearrange this equation to solve for number of moles. To do that, I'm going to get the pressure of argon times the volume of the system divided by my gas constant times the temperature. My pressure is in millimeters of mercury, so I do need to convert that to atmospheres, because that happens to be the gas constant I choose to use. So 277 millimeters of mercury times 1 atmosphere per 760 millimeters of mercury. You should be able to convert through all the different units of pressure, so you should be able to use any gas constant you want to use. Divided by 0.08206 liter atmosphere per mole K. And the temperature, 125, is 398 K. I calculate this out and I get 0.1116. I'm going to hold on to one extra sig fig right now, moles of argon. I just don't want to create rounding error if I don't have to. It's always good to make sure everything's canceling. So millimeters mercury cancel with millimeters of mercury, atmosphere with atmosphere, liter with liter, kilogram or Kelvin with Kelvin, and I've got moles in the denominator of a denominator, which means it moves to the numerator. Now that I've got my moles of argon, I can quickly figure out the number of grams of argon. 0.1116. I usually I'm underlining that third one because that's where my sig figs are. Multiply that by the atomic weight of argon, 39.95 grams to 1 mole. And I get 4.46 grams of argon. So my mole fractions and my number of grams of argon in this mixture. Let's look at another example. What is the partial pressure of oxygen in a mixture that contains 0.30 moles of O2, 0.70 moles of N2, and 0.25 moles of argon if the total pressure of the system is 1.1 atmosphere? Well, first, I've got 0.30 moles of O2, 0.70 moles of N2, 0.25 moles of argon, total pressure of 1.1. I need to find my mole fraction. I want partial pressure of oxygen. So I'm trying to find PO2. PO2 is equal to my mole fraction of O2 times the total pressure of the system. I have this, I want this, I'm going to calculate this quick. I know my partial pressure, or my mole fraction of O2 is equal to my number of moles of O2 divided by the number of moles total. So number of moles of O2 plus number of moles of N2 plus number of moles of argon. I have 0.30 moles of O2, dividing this by 0.30 moles of O2, plus 0.70 moles of N2, plus 0.25 moles due to argon. My mole fraction here is 0.24. Again, no units there, moles have canceled with moles. All of these add up to 1, so I've got moles divided by moles. My pressure of my O2 in this system, mole fraction of O2 times total pressure of the system, 0.24 times 1.1 atmosphere. This is 0.26 atmosphere. So our answer is E. Another application of Dalton's law is if a gas is collected over water. So if you've got a system, you're doing a reaction collecting the gas, but it's collected over water, there's also going to be water vapor present along with the gas you produce. In order to calculate the correct pressure here, you need to subtract out the water vapor. This changes with temperature, so water vapor is temperature dependent. I will give you those values. You are not required to know them. We get them from tables. But you have to subtract out that water vapor, which changes again with temperature, from the measured atmospheric pressure to find the partial pressure of your gas. So because what's happening is the water vapor is adding to it, we need to subtract that out to figure out what your actual partial pressure is. So let's see an application for that. I've got a couple different types of examples here. Number 1, calculate the volume of a gas that could be collected over water when 6.75 grams of aluminum reacts with excess hydrochloric acid solution at 0.985 atmospheres and 15 degrees C, assuming a 90% yield. So there's lots going on in this question. We want the volume of the gas. We see it's collected over water. We've got 6.75 grams of aluminum reacting with excess HCl at 0.985 atmospheres, 15 degrees C, and we've got a 90% yield to consider. So, at 15 degrees C, the vapor pressure of water is 0.0168 atmospheres. And again, on an exam or a quiz, I would give you that value. Homework, you guys can look that up. My pressure tells me that I am at 0.985 atmospheres. But I need to subtract out this value due to the water vapor that's being absorbed as well. So minus 0.0168 atmospheres equals 0.968 atmospheres, the actual partial pressure for my system. Temperature, 15 degrees C, convert that to Kelvin, I get 288 K. I also see that I have aluminum reacting with excess HCl. That means that aluminum is my limiting reactant. I need to find the number of moles of aluminum. So number of moles of aluminum, I've got 6.75 grams of aluminum times 1 mole of aluminum. Aluminum weighs 26.98 grams per mole. And let me check that number quick. Let me write that down. 6.75 divided by 26.98 gives me 0.250 moles of aluminum. Now I have all my pieces. I can go ahead and use the ideal gas law. PV equals nRT. I've got P, I've got N, I've got T. This is a constant. I'm trying to find volume. So rearrange the equation to solve for volume. V equals 0.250 moles of aluminum. Gas constant 0.08206 liter atmosphere per mole K. Temperature 288 K. And the pressure 0.960 atmosphere. And I need to calculate this out quick. 1 sec. 0.25 times 0.08206 times 288 divided by 0.968 gives me 6.10 liters. So moles to moles, atmosphere, atmosphere, K, Kelvin, Kelvin. I've got liters. We are good. But the last trick to this is it says assuming a 90% yield. So 90% yield, that means I get 90% of this. So 0.90 times 6.10 liters. 0.9 times 6.10 gives me 5.50, or depending on how you run, 5.49 liters that will actually be produced. So the volume collected over water would be 5.49 liters. And what gas are you actually collecting here? Hopefully you guys recognize that too. You are collecting H2 gas. What mass of water vapor is produced? So this time I'm looking for the mass of water vapor from a gas phase reaction of O2 with H2 in a 2.5 liter container, 28 degrees C, if the partial pressures of O2 and H2 are 0.98 atmospheres and 1.24 atmospheres respectively. What I need you to recognize on this question is that I have 1.24 atmosphere, 0.98 atmosphere. I have values for both reactants. Therefore, I have a limiting reactant problem or a limiting reactant example. First thing I'm going to do is find the number of, I'm going to find the number of moles of each reactant I have, and then ask myself, do I have enough of one reactant to be able to actually react all of the other one? Figure out what my limiting reactant is, basically. So let's see, number of moles of H2. How am I going to find this? PV equals nRT. So I'm going to solve for number of moles, PV over RT for each one. For hydrogen, I have a partial pressure of 1.24 atmospheres. My volume is 2.5 liters. Gas constant, 0.08206 liter atmosphere per mole K. And my temperature, 28 degrees C, but in Kelvin, is 301 Kelvin. This gives me 0.126 moles of H2. I'm going to do the same thing for oxygen. Number of moles of O2, 0.98 atmospheres, 2.5 liters. 0.08206 liter atmosphere per mole K and 301 Kelvin. This is going to give me 0.0992 moles of O2. So I know I have 0.126 moles here, 0.0992 moles here. You have to see which one your limiting reactant is. Some students will automatically say O2 because it's a smaller number, but realize you're reacting 2 moles of hydrogen gas, H2, for every 1 mole of O2 reacted. So you have to do the stoich to see which one really is your limiting reactant. I'm going to write that up here. So the question I'm going to ask is, do I have enough O2 to react all H2? How do I find that? Well, how many moles of O2 do I need to completely react all of my H2? Again, why am I picking H2 to see if I can react it all? Because I know I need 2 moles of H2 to 1 mole of O2. So it's a gamble here. Which one is going to be the right one? 0.126 moles of H2. Convert that to moles of O2. 1 mole of O2 is required to react 2 moles of H2. I get out an answer of 0.63 moles of O2. This is the moles required to react all of my H2. Compare this number to what I've got. And the answer is yes, I have enough. That means that H2 is my limiting reactant. Now that I know what my limiting reactant is, I can use the number of moles of my limiting reactant to see how much water vapor will actually be produced. So the number of grams of water is going to be dependent upon that 0.126 moles of H2 I'm going to have, or I'm reacting. 0.126 moles of H2 form 2 moles of water for every 2 moles of hydrogen. Water has a molar mass of 18.02 grams per mole. Remember, it's asking for mass here. Mass is not moles. Moles is a number. Mass is a grams is a mass. 2.27 grams of water vapor will be produced. So we figured out what our limiting reactant was, and we used that to see how much of our product could we actually make. And the last example in this section, how many moles of acetylene are present in 500 ml sample of gas collected over water at 20 degrees C with a total pressure of 758 torr. The vapor pressure of water at 20 degrees C is 17.54 millimeters of mercury. So I'm trying to find moles of acetylene, 500 ml sample, gas collected over water, 20 degrees C, total pressure of 758 torr. Vapor pressure of water at 20 degrees C is 17.54 millimeters of mercury. 20 degrees C in Kelvin is 293 K. There is 0.0 there, so I would say 293.2 K. 500 mils, I need that in liters, 0.5000 liters. I know that my total pressure is equal to my pressure of acetylene plus my pressure of water. The pressure of acetylene is equal to my total pressure, so 758 torr, minus my pressure from the water, 17.54. This does say millimeters of mercury, but remember 1 torr equals 1 millimeter of mercury. So you can either put this in torr millimeters of mercury, so 17.54 torr. And let me calculate that out quick. 758 minus 17.54 gives me 740.46. My sig figs are here at the 0, but I'm going to hold on to this for right now. This is torr. Now I'm going to convert that to atmospheres. You can convert whenever you want. I prefer to convert at the end. 1 atmosphere is 760 torr. Again, you could have converted everything to millimeters of mercury as well. I don't care. As long as you're dealing with the same units. 0.969 atmospheres. Now I'm ready to find the number of moles. So the number of moles of acetylene is equal to the pressure of acetylene, 0.969 atmospheres. Volume of your system, 0.5000 liters. Don't want to forget sig figs there. Gas constant, 0.08206 liter atmosphere per mole K. And your temperature, 293.2 K. This equals out to 0.0203 moles of acetylene. So how many moles can I produce? I can produce 0.203 moles of acetylene. That is the end of the section on Dalton's law of partial pressures.